Hi everyone, and welcome back. So, today we're going to be talking about curvilinear motion. Oh, there it is. For cylindrical components. I probably don't need to underline everything, but hey, why not? I can do it if I want. Okay, I won't do everything. So, what we're going to be able to do? Well, determine velocity and acceleration components using cylindrical coordinates. Why does that matter? Because some systems are cylindrical, and it just makes a lot more sense to deal with them in that coordinate system. So let's get into some applications. So first off, we use cylindrical coordinates in cases where we have a 3D curve that is cylindrical. In this figure shown, we see we have some box which is going down a very, very large helical ramp. Now, question for you is, how do we know if this box is going to fly off the ramp? It's constantly going to be trying to tip outward because of the curve. So how fast can it go before it flies off? And how would you know that? How would you determine that? Because this is different than our previous example. You know, we can't just say, well, okay, we have a circle that makes things nice and easy. No, we actually have a z-coordinate as well. What to think about this? Or this child right here. This girl's on the slide, and if you look at it, well, she's not, like, hopefully, going to go any further out than that or further in. Obviously going to go further in. So her radial coordinate is constant. However, the transverse coordinate increases with time. And her altitude, z, decreases with time. Is there a way we can use this to describe her motion, to figure out the velocity and acceleration components, and also just to understand what her position is with time and how it changes? So once again, acceleration is a good question. Will she fly off the slide? It's got a pretty high wall here, which does help, but if there was no wall, would she fly off the slide? Well, how would we tell this? We would do it by making a cylindrical coordinate system. So to do that, what we start with? Well, we start with our position vector. We have some origin. The origin is not necessarily on U. This is not the same as the NT coordinate system, though there will be some similarities at points. No. What we have here is we have a origin, which is off in the distance. It is not on my object that is moving. And there is a position vector R. Now, in this case, I'm looking at it from a 2D situation. And while my origin is fixed, my position vector goes to this point, and there's some angle from a particular axis, maybe the x-axis right here, or the y-axis, or just some plane of reference. There is an angle theta from that reference. Then we get two components of my position. One is directly along this r vector right here. And the second one is my angle theta. I'm going to need that right here. I need that angle theta. So if you're looking at it in this way right here, and this is my coordinate system, my coordinate axes, you can see that my position is entirely r. However, I'm looking at velocity components. Obviously, there's going to be a theta component as well as an r component. So we're looking at the velocity. Well, what do we have here? We have two components. We have our magnitude r and our unit vector u of r. Now, if you're looking over here at this system, you can see that those both are going to change. The magnitude r is going to change as well as the direction that u of r is pointing. So when we take our time derivative, we can't just say, well, r is constant or my unit vector r is constant. No, they're both going to change. And so we have to use the chain rule to get them out. So first d last plus last d first, or vice versa. And so you see right here we kept our u of r constant, and we took the time derivative of our magnitude of our vector, which gave me r dot. Second one, we kept r constant and took the time derivative of our position vector in the r direction, the radial direction. Now, we use the chain rule to figure out what this actually is, in terms of something we actually know. So, using the chain rule, we realize that we can rewrite this, if we want to, in terms of u theta. Now, how do we do that? Well, small angle approximation is going to say that dur d theta is equal to u theta. Okay. So since we're going to an infinitely small interval, it works. So since we know that this right here is u theta, I should make that subscript. There we go, u theta. Perfect. We can simplify this. And so what it comes down to is our velocity is going to be equal to the time derivative of our position times the radial vector plus our radius times our time rate of change of our angle theta times the theta unit vector. So we have two components here, two components to the velocity. If we want to take the magnitude, we can to get our overall velocity, the magnitude of our velocity at any particular point. Now, as you can see in this little one right here, the velocity is always going to be tangent to the curve that's going on. However, both of these components will not necessarily be. So, let's stop here, and I'll see you all next time. Thank you so much for listening. Bye-bye.